These beers, by the way, are made out of beryllium, which is a wonderful material at 40 Kelvin where this thing operates. Okay, how are we doing on time anyway? We're doing okay. Okay, now another mission that is flying right now. It's called Kepler. It's taking a census of Earth-like planets around other stars. It's looking out a place in Cygnus at a field of view. It'll stare there for 3 or 4 years, the same field. 5,000 or so stars in there that they're looking at. And if an Earth-sized planet passes in front of one of those stars while it's staring, the light dips very slightly, maybe 1 part in 100,000, so very slight. But it has the sensitivity to see that. So and what it does, it stares at that field, just stares. And if it sees a star light dip a little bit, so, oh, maybe something happened. But there's noise too. If it sees it again sometime later, oh, maybe that's a planet went in front of it. If it sees it a third time at the same period, then it's we have verified, we have detected an Earth-like planet, and the ones they're looking for are in what they call the habitable zone, where it's the theory is that if there's life out there, life other than ours out there, that it's going to require water in a liquid state. If it's too hot, if it's a gas, it won't, or if it's too cold, it'll freeze. So the theory is life will require that. So they speak of that as the habitable zone. And I designed the optics on this in 1993, and we kept proposing it. And it's a difficult design. It's a large field of view, 12 degrees field of view, and it required a very large aperture and a short focal length to make it, in optical terms, it's a fast system. And part of the thought, I will put this up here because it's part of the thought process of this. I looked, I've been working for years, but I go back through my files. I looked at 50 different ways of doing it. Wide field systems, 50, and I looked and did trade-offs between them, and I came up with this. It's called a Schmidt, and there are Schmidts everywhere. A Schmidt has a spherical primary mirror, and at the center of curvature is what they call the aperture stop. The light comes through that, and because it's a sphere, it has no off-axis aberrations because everything is symmetric. And then they put they put a corrector in to fix another aberration, spherical aberration, and then it formed an image down here on a curved surface that's symmetric with the sphere. So I finally settled on that, and it was more complicated than I liked. This plate out here is 4 centimeters thick and 1 meter in diameter, a big piece of glass. But it was the best I'd come up with, and the science team had some other consultants look for ideas. It was the best they come up with. So that's what we're flying. It's flying right now. And the key was to go back to basics. Look at the very basics. Go back to there. Don't assume the first thing you think of. The focal plane, and I believe the speaker last year talked about the focal plane. The focal plane has 82 million pixels in it. They're segmented like this. Each has a lens, a field flattener lens to flatten the field on that focal plane. And so it's there, and this thing just stares. It just stares and stares and stares. I dug up, Google's good. I dug this up. This was as of October 5th. They had found 6 potential habitable planets. Let's see, unconferred potential is 27, moons around them are 30. This is their best, 1.6% is their best estimate from this of what fraction of stars have planets, have habitable planets. So, and that's a very important number for planning future missions to image an Earth around another star. There are now, these are big planets too, there are now 839 confirmed planets. That's pretty good, little planets out there. And a lot of these were detected by doing by ground base, by Jeff Marcy doing at Santa Cruz doing ground-based observatory, but we don't need to go into that. But so anyway, okay. You know, I had fun. I had fun. I still have fun. But doing these things and doing your thing, it's very demanding. I mean, day and night and day, years on end. I'd go on vacations and I'd come back early. I mean, just the mind never stops, But I loved it. I loved it. I loved it at Ball when there were chances, when there were opportunities. I loved it at Lockheed where there were opportunities. If there are not opportunities, it got very boring. But and this stuff was these space missions were opening the world to stuff we didn't know about. So I had a lot of marvel at the physical world, and I still have that. We're driving out here from Colorado. The leaves turning. I mean, there's just a lot of good stuff out there, and I enjoy that. The mind is still working, and it's enjoyable, and that's what leads science. I think that's what leads scientists to do what they do. Rick Bottom and I, the fellow I worked with a lot, would say, well, let's learn something new every day. Or we would figure something out and say, oh, we learned something today. That was very important. I was bored until the work became both worthwhile in my mind and challenging. I bore pretty easily. And I was constantly reading, learning anything, go to conferences, read books, because things change. And what you learn here won't be there when you get out, or 5 years from now. But you'll learn, but what you'll learn here is how to learn those things, how to absorb them, how to understand them. For me, I had to do something that I felt was socially important, it was meaningful. That meant staying away from defense things for me, and working on, on science to advance knowledge and technology. I did a lot of that. I have 3 patents, and and other things, and these instruments. I mean, there's always some little problem to fix, and there's all something new. And working with the top scientists, very inspiring, very, very nice people, extremely nice people, and very inspiring. And they encourage, yeah. Technology, well, we have our cell phones now, and science makes that contribution. So about ready to wrap up here, I think. I asked myself the musical question: how did education provide the tools so I could stay current with science and technology? And the number one thing was that I came up with was how to solve a problem, how to look at something that I did not understand and discard the the meaningless parts, the parts that didn't matter, and look at the parts that did matter, how to critically think my way through the problem. Isolate the real issues. You can spend a lot of time working on the non-important issues, but get to the real issues. And I learned that. I learned that here at Kansas State. I learned that from some failures too, but I learned that here at Kansas State. How to critically think, how to determine that, and also very important, how to check what you've discovered. You may solve the problem, and then if you don't check it, you may later find out that you really didn't solve the problem. So it's really important to check it. Okay. Knowledge really does advance. Now, I was amazed to find out that until around 1930, when Edwin Hubble made his measurements, the world thought there was one universe and it was static. There was one galaxy, I'm sorry, and it was static. The whole universe was our galaxy. Einstein even put a fudge factor in his general relativity equations to make them static. Hubble discovered that things were expanding and that there were more galaxies. So that was only 40 years, 30 years before I started studying physics. Around 1960, I don't know what the estimate was on galaxies then, but I know that the thought was the universe was expanding and there were a lot of galaxies. We could see them. 40 years since then, well, it's still expanding, but we have no understanding of what's happening out there because 1998-ish, with a GRISM-on advanced camera and other measurements, they found this great sucking, this negative pressure that the universe is expanding faster than what was predicted. They refer to that as dark energy. And who knows? No one, this is now a top science priority because it gets into particle physics and cosmology and everything. Now with these deep surveys, they can estimate, here we had one galaxy. There are somewhere around 100 billion galaxies. And somewhere around, within factors of a few, around 10 to 23rd, that's a big number, stars. One with 23 zeros, I guess. And I find it interesting that that's very close to Avogadro's number, which is, and that's chemistry. Anyway, so where will the state of knowledge be in 50 years? I don't know. It's really expanding, but I would love to know. I'd love to be there. If I could live to be 117, maybe things that happen, I could do that, but you will be there. You will be there. And this will be your reality. You will know these things because of things you're learning here and because of what you're applying to yourself and because of your brilliant minds. So anyway, I'm wrapping up here. Again, I had, Ken Ohm was my high school physics teacher. First year, he was the first year teacher. I took physics under Ken, Mr. Ohm. And he just turned me on to physics. And I held on to that. I did not contact him until, maybe half dozen years ago. I looked him up on Google. Google's a miracle. So anyway, teaching physics and astronomy at Washburn. So I'm so happy that you're here, Ken, and meet your wife. So I thank you. I thank Kansas State and the physics department. I got a very sound and thorough education here. I got the basics very well here. And I also, there's really no higher honor than being honored by your peers, and this is what this is for me. So.